This paper proposes high-performance CPU cloth simulation using domain-decomposed projective dynamics. Our approach leverages domain-decomposed projective dynamics to maximize the computational efficiency of multi-core CPUs while maintaining high-quality simulation results. We started from partition the domain from garment patterns. The vertices are categorized as corner, duplicate, and internal vertices, leveraging the problem into a dual variable solving and a primal variable processing on each domains in parallel. Here are some results with our method. On this case, the character in a fitted t-shirt and shorts performs a single handstand dance. There are 376,000 degrees of freedoms and 234,000 elements involved. On this case, the character dresses with a tight white nightdress and performs a hip-hop dance on the spot. There are 390,000 degrees of freedoms and 256,000 elements involved. The simulation runs at 395 milliseconds per time step. In this scene, a character wearing a loose, multi-layered long dress performs a throwing motion. The simulation runs at 351 milliseconds per time step. On this case, the character dressed in a robe is swaying and whirling in place. There are 519,000 degrees of freedoms and 343,000 elements involved. The simulation run at 374 milliseconds per time step. Here we show a high-resolution simulation involving 6 million degrees of freedoms. Each curtain has 32 domains as shown. They are pulled away from the middle to reveal the view of a city night. The simulation runs on 6.6 seconds per frame on average. In this scene, 4 tablecloths fall on the table one by one with different orientations. When stacking on each other, complex self-collisions are generated. There are 492,000 degrees of freedoms in the system, and the simulation runs at 557 milliseconds per frame. Here we compared our method with most recent state-of-the-art nonlinear simulation solvers on GPU or CPU. Here are some results. On this example, the character in a tired skirt performs a kicking action. With our method, it is 2.6 times faster than GPU-based PDBFGS and 66 times faster than multi-core accelerated CPU CIPC. Here we also compared our method with PD Coulomb. Both using PD framework, our method can integrate with the friction model, while performed with above an orders acceleration. On this experiment, we compared our method with GPU-based PD-IPC solver. We pull 2 strips in opposite directions to create a tight knot. Our method uses 560 for milliseconds on average for one time step, while PD-IPC use 540 for milliseconds. We compared our method with PD-EXP, which is also a GPU solver. The character is performing a fashion show. There are 1.1 million degrees of freedoms. Our method runs at 1.1 second per frame, which is slower than PD-EXP. While our primary focus is high-resolution cloth simulation, our method can also be used to simulate volumetric deformable models. On this scene, 2 dressed armadillos fall into a container. On average, each time step takes 200 for milliseconds. On this scene, the barbarian ship slides down on a spiral stair. There are 487,000 tetrahedron elements on the ship, which is decomposed into 64 domains. Our method uses 379 milliseconds to simulate one time step on average. Thanks for your attention.